Part 1. Newton's Paradox and the Massless Nature of Light. Chapter 1. Introduction. The Gravity of Mass. From our earliest days in school, we are taught the fundamental logic of Sir Isaac Newton. Gravity is a pull between objects with mass. The apple falls to the ground because it has mass. The Earth orbits the Sun because both possess immense mass. In Newton's universe, the formula for universal gravitation, F equals G times m1 m2 divided by r squared, dictates that if an object has no mass, m equals 0, the gravitational force acting upon it must be 0.
Chapter 2. The Problem. Light as a Weightless Wanderer. Enter the photon, the fundamental particle of light. Modern physics confirms that a photon has zero invariant mass, rest mass. It is, in a sense, a proletarian of the material world, possessing energy and momentum, but completely lacking the physical weight that Newton's laws require for gravity to take hold. Chapter 3. The Conundrum. The Ultimate Free Agent? According to Newtonian logic, light should be the ultimate free agent of the cosmos. It should travel in perfectly straight lines, indifferent to the gravitational tug of planets, stars, or galaxies. If gravity requires mass to exert a pull, light should be invisible to the reach of gravity. Chapter 4. The Reality Shock. The Eclipse that changed everything. In 1919, the world of physics was rocked to its core. Sir Arthur Eddington, a British astronomer, traveled to the island of Principe to observe a total solar eclipse. His goal was to test a radical new theory. As the moon blocked the sun's glare, Eddington photographed the stars appearing near the sun's edge. The results were undeniable. The positions of the stars had shifted. Their light, passing through the gravitational field of the sun, had been bent. This posed a staggering question. How can something with no mass be pulled by gravity? Chapter 5. Expanding the Narrative with Scholarly Context. To understand why this happened, we must look beyond Newton to the records of the Royal Society and the breakthroughs of Albert Einstein. Einstein's thought experiment. Years before the 1919 expedition, Einstein realized that if a person in a falling elevator turned on a flashlight, the beam would appear to bend upward to an outside observer. This led to his equivalence principle, suggesting that gravity and acceleration are indistinguishable. The curvature of spacetime. Einstein proposed that gravity isn't a pulling force at all. Instead, massive objects like the sun warp the very fabric of the universe, spacetime. Imagine placing a bowling ball on a trampoline. It creates a dip. If you roll a marble or shine a laser across that trampoline, it follows the curve of the fabric. The 1.75 arcseconds verdict. Newton's theory actually did allow for a slight bending of light if one treated light as particles with mass, but it predicted a very small deflection. Einstein's General Relativity predicted a deflection exactly twice as large, 1.75 arcseconds. Eddington's 1919 data matched Einstein's prediction, proving that light doesn't bend because it is pulled, but because the road it travels on is curved. Space tells matter how to move. Matter tells space how to curve. John Archibald Wheeler, summarizing Einstein's legacy. Part 2. The Historic Leap. When Einstein challenged Newton. Chapter 1. Newton's Achilles heel, the mystery of action at a distance. For over 2 centuries, Sir Isaac Newton's laws reigned supreme. His equations were, and still are, precise enough to calculate satellite orbits and land humans on the moon. However, Newton himself was haunted by a fundamental flaw in his theory. He had no idea how gravity actually worked across the vast, empty vacuum of space. How could the sun exert a pull on the Earth across 150 million kilometers of nothingness instantaneously? Newton famously wrote in Principia, "Hypotheses non fingo, I frame no hypotheses," essentially admitting that while he could calculate the force, the underlying mechanism remained a total mystery. Chapter 2. Einstein's Revolutionary Answer, 1915. The breakthrough came in 1915 when Albert Einstein published his general theory of relativity. He boldly declared that gravity is not an invisible tug-of-war force acting at a distance. Instead, Einstein redefined gravity as a structural feature of the universe. Gravity is the curvature of spacetime. Chapter 3. The classic illustration, the fabric of the universe. To visualize this radical shift, physics educators often use the rubber sheet analogy. Imagine a flat, stretched rubber sheet representing empty spacetime. If you place a heavy lead ball, the sun, in the center, the sheet curves and forms a dip or a gravity well. When you roll a smaller marble, the Earth, across the sheet, it doesn't move in a circle because it is being pulled by a string. It orbits because it is following the slope of the curvature created by the heavier mass. Chapter 4. The conclusion. A change in perspective. Einstein's genius was realizing that the sun doesn't reach out to grab the Earth. Instead, the sun's massive presence simply warps the geometry of the space around it. The Earth is merely traveling along the most natural, straightest path possible, known as a geodesic, through a space that has been bent. In this new light, gravity isn't something that happens to objects. It is the very shape of the arena in which they move. Part 3. Why does light steer into a curve? Chapter 1. The theory. Mass is irrelevant. It is an established fact in modern physics that light has no rest mass. However, in the realm of general relativity, this weightlessness does not grant light immunity from gravity. This is because gravity is not a selective force that only grabs matter. It is a property of the environment itself. Since light must travel through spacetime, it is forced to follow whatever shape spacetime takes. Chapter 2. The Geodesic. Redefining the straight line. In a flat universe, the shortest distance between 2 points is a straight line. But in a curved universe, that definition changes to a concept called a geodesic. A geodesic is the path that an object follows when no other external forces, like friction or an engine, are acting upon it. Light is the ultimate perfectionist. It always takes the shortest and most efficient path through space. When a massive object warps the space around it, the shortest path is no longer a straight line in the traditional sense. To an outside observer, the light appears to bend, but from the light's own perspective, it is traveling as straight as the warped road allows. Chapter 3. Real-world evidence. The Great Circle Route. To understand this counterintuitive logic, we can look at global aviation. If you look at a flat 2D map, a flight from Beijing to New York appears to follow a massive arc that curves toward the North Pole. On a flat map, this looks like a detour. However, because the Earth is a sphere, that curved arc is actually a great circle, the mathematically shortest distance between those two cities. Just as a pilot follows the curvature of the Earth to save fuel and time, light follows the curvature of space-time, because that is the path of least resistance. Chapter 3: Real-World Evidence, the Great Circle Route. To understand this counterintuitive logic, we can look at global aviation. If you look at a flat 2D map, a flight from Beijing to New York appears to follow a massive arc that curves toward the North Pole. On a flat map, this looks like a detour. However, because the Earth is a sphere, that curved arc is actually a great circle, the mathematically shortest distance between those two cities. Just as a pilot follows the curvature of the Earth to save fuel and time, light follows the curvature of space-time, because that is the path of least resistance. Part 4: Undeniable Proof. Reality Checks for the Skeptics. Chapter 1: The 1919 Solar Eclipse, the moment Newton was dethroned. In the early 20th century, Einstein's theories were seen by many as mere mathematical fantasies until Sir Arthur Eddington provided the smoking gun. During the total solar eclipse of May 29, 1919, Eddington measured the positions of stars as their light passed near the sun. While Newton's physics predicted a slight deflection, Einstein's General Relativity predicted an angle exactly twice as large. When the data confirmed Einstein's specific 1.75 arcseconds of deflection, it sent shockwaves through the world. The London Times famously announced the news with the headline, "Revolution in Science: Newtonian Ideas Overthrown." Chapter 2: The GPS in Your Pocket. Einstein's Daily Presence. You don't need a telescope to see evidence of general relativity. You only need to open Google Maps. The GPS satellites orbiting Earth experience a slightly weaker gravitational pull than we do on the surface. According to Einstein, this means time actually moves faster for the satellites, by about 38 microseconds per day. While that seems insignificant, if engineers did not calibrate the clocks using Einstein's equations, the positioning on your phone would drift by about 10 kilometers every single day, making the system useless. Chapter 3: The Shapiro Delay, 1964. The Long Road Through Space. Decades after Einstein's death, Harvard physicist Erwin Shapiro proposed a new way to test the stretching of space-time. He sent radar signals from Earth to Venus and Mercury just as they passed behind the Sun. He discovered that the signals took slightly longer to return than expected. This wasn't because the signals slowed down. Light always travels at its constant speed, but because the Sun's gravity had dented and stretched the fabric of space itself. The light was simply traveling a longer, curved path through the gravity well of the Sun. Chapter 4: Key Evidence Summary. 1. Eddington Expedition. Year 1919. Proved light follows the curvature of space-time. 2. Shapiro Delay. Year 1964. Confirmed that gravity stretches the distance light travels. 3. GPS technology. Modern. Real-world application of time dilation and gravitational shifts. These discoveries transformed Einstein's work from a radical theory into the very foundation of how we understand the mechanics of our universe. Part 5. The Extreme Limit, Blacker Than Black. Chapter 1. Black Holes, the ultimate warp. If the sun creates a dip in the fabric of spacetime, a black hole creates a bottomless abyss. It is a region where spacetime is warped so severely that the laws of physics as we know them reach their breaking point. At the event horizon, the point of no return, the curvature becomes so steep that every possible path, even for light, leads to only one destination, the center of the black hole. Not even the fastest entity in the universe can escape this geometric trap. Chapter 2: Gravitational Waves, 2015. Hearing the Fabric Ripple. In 2015, the LIGO, Laser Interferometer Gravitational Wave Observatory, confirmed another of Einstein's radical predictions: gravitational waves. When two black holes collided 1.3 billion light-years away, they sent ripples through the fabric of space-time, much like a stone thrown into a pond. To detect this, scientists used light, lasers, to measure a change in distance smaller than 1,000th the diameter of a proton. This monumental discovery proved that space-time is not a static void, but a dynamic, vibrating stage. Chapter 3: Conclusion. Gravity does not care about the weight of light. It doesn't need to pull on a photon to change its direction. Instead, gravity dictates the very stage upon which light performs. By observing how light bends and shifts, we are actually reading the language of the universe, allowing us to feel the curves, ripples, and vibrations of the deep cosmos. That concludes our journey of discovery today at Nok Lik Studio. We hope this glimpse into the warped reality of our universe has left you as fascinated as we are. See you in our next exploration. If you enjoyed this video, please give us a like, share it with your fellow space enthusiasts, and subscribe to our channel. Your support is the greatest motivation for us to keep bringing the mysteries of the universe to light. Thank you so much.